Swayam Prabha. Digital India. Educated India.
Good morning. Starting from this lecture, in a few lectures we will cover the classical topics of numerical analysis: function interpolation, then numerical integration and numerical solution of ordinary differential equations. First, in this lecture we discuss interpolation and function approximation. The widest used interpolation of functions is through polynomials. So, first we discuss polynomial interpolations. The problem here is to find an analytical representation of a function from information at a finite number of data points. For example, suppose you have got a function of x for which you have data regarding the function at several data points, say here, 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 here and here, and from that you want to develop the function in the form of an expression, so that with that expression you can develop the function continuously and evaluate the function at any point in between. Okay. So, that is called function interpolation. Now, the purpose is to evaluate at arbitrary points at which the data is not there, and apart from that, if you have an analytical representation in the form of an expression, then you can differentiate or integrate the function as the need arises. Besides, once you have an expression for the function, you can draw certain conclusions regarding the trends of the function or nature of the function. So, with these purposes in mind, we try to develop analytical expressions, analytical representations of functions from information available at discrete data points. Perhaps those discrete information can be obtained from experimentation or through some other computation, which cannot be conducted at infinite points. Now, interpolation, which we are going to consider now, which we are going to discuss now, is one of the ways of function representation. There are other ways also, and in the interpolatory approximation of a function, the sampled data, the data which is given, are exactly satisfied. Now, polynomials offer a convenient class of basis functions, as linear combinations of which we can express the function quite easily. So, in a particular problem, suppose y I as f of x y is available at these n plus 1 points, x0, x1, x2, x3 up to xn. With the help of these n plus 1 pieces of data, we want to fit a polynomial of the nth degree. Now, why nth degree and n plus 1 points? Because a polynomial of nth degree will have n plus 1 coefficients, the determination of which will require n plus 1 pieces of data, and that n plus 1 pieces of data you get from the function values at these n plus 1 points, starting from x0 up to xn. Now, the task of formulating or finding this polynomial is basically the determination of these a1, a2, a0, a1, a2 coefficients, which will match the given n plus 1 pieces of data exactly. That is interpolation. And after that, at any other value of x in this interval, if we try to find out the value of px from this polynomial, that will in a way represent the function f at that point, and this is what is called interpolation. finding the value at an in between point. If based on this same expression, if we try to find out the function value or estimate the function value at a point outside this interval, such an activity is called extrapolation, which for all situations is not considered safe and reliable enough. Now, one question arises that for given values n plus 1 values of the function at n plus 1 points, can we always find a polynomial of the nth degree like this? And the other question that arises that if we can find, then will a single set of values for these coefficients will be found, or whether we can find multiple sets of values for these coefficients. That is this polynomial fitting this data unique? First of all, whether it exists for all data of this sort, and whether that is unique, whether the polynomial exists which will interpolate these data, and whether that polynomial is unique. Now, if we just try to insert the values of x0, x1, etc. in this and equate the corresponding expressions to y0, y1, etc., then we get n plus 1 equations in these coefficients. These equations are here: a0 plus a1 x0 etc. up to an x0 to the power n equal to function value at x0 and so on. Now, the values of a0, a1 up to an will exist and they will be unique if this coefficient matrix is non-singular. Now, this particular matrix with different values of x0, x1, x2, x3 etc. is a well known matrix known as the van der Monde matrix, and it is known to be invertible. You can analytically show that it is invertible, but then it is typically ill conditioned. Now, you can analytically show it is invertible, but here we will not take up that exercise, because we are going to establish the invertibility of this matrix, that is existence and uniqueness of these coefficients, that is the polynomial, through some other shortcut means. So, therefore, we will not spend our time on formally showing that it is invertible. From the existence and uniqueness of the polynomial coefficients, the invertibility will be established. But keep also in mind this fact, that is, even though this matrix is invertible, but typically it is ill conditioned. That is, the solution process will quite often have numerical errors because of the ill conditioning. Now, we try to see the uniqueness of this polynomial coefficient set. Suppose there are two polynomials, that means two sets of values for these coefficients which match the function values at the given data points, and those two polynomials are p1 and p2. Now, what can we say about p1 minus p2, that difference polynomial? Now, p1 is an nth degree polynomial, p2 is also an nth degree polynomial. So, their difference will be at most an nth degree polynomial. Now, at n plus 1 data points, p1 matches it exactly. That means, at those n plus 1 points, the p1 polynomial p1 will have exactly these values, p2 also. So, the difference of these two polynomials will have 0 values at n plus 1 points. That will mean that delta px is an nth degree polynomial of x, but at n plus 1 values of x, it has got 0 value. Now, you know from the fundamental theorem of algebra that an nth degree polynomial will have exactly n roots. It cannot have n plus 1 roots, right? And that means that if delta p satisfies such a requirement, that will mean that it is not only 0 at those n plus 1 values, but it is the 0 polynomial. That means the entire polynomial is 0. That means all the coefficients are 0, which will mean that delta p is 0 as a polynomial will mean that p1 and p2 are actually the same polynomial. That shows that px is unique, and px exists, that we can argue based on the properties of linear system of equations. But let us go another round, and existence also we establish in a little shortcut argument. How? For that, we do something which we would have done otherwise also, because we know that solution of this will require us to solve an ill conditioned system. So, typically we may not like to do that for large value of n, that is for high degree polynomial. So, what we can do? The alternative is Lagrange interpolation. For that, we consider the basis functions not as 1 x, x square, x cube, the way we did last time. Okay. In this function representation, the basis functions were 1 x, x square, x cube, etc., and coefficients were a0, a1, a2, etc. So, we have noted that with this kind of a polynomial expression, it will be very easy to differentiate and integrate, etc. Okay. But then evaluation through the solution of this kind of a system is going to be unnecessarily time consuming. So, what we can do is that we can use basis functions not as 1 x, x square, etc., but this kind of basis functions. Examine carefully. In this expression, we have got in the denominator product of xk minus xj, j running from 0 to n, except j equal to k, of course, because for j equal to k this will become 0. So, that term we do not have, all other terms we have. Now, in the numerator, in place of xk we have x. So, the denominator is a constant number. So, that means for the second basis function k equal to 2, okay, we have got here x2 minus x0, x2 minus x1, x2 minus x3, x2 minus x4, and so on up to x2 minus xn, and that is a number. In the numerator, we will have the corresponding x minus x0, x minus x1, x minus x3, x minus x4, etc., up to x minus xn, omitting x minus x2. Okay. So, that means that this numerator is an nth degree polynomial in x, denominator is a number. So, L2x is an nth degree polynomial. Similarly, L0, L1, L2, L3, L4, all of them will be nth degree polynomials. Okay. So, we have got n plus 1 nth degree polynomials. Okay. So, any linear combination of them also will be an nth degree polynomial, and this is the linear combination. Now, here the basis functions are these functions L0, L1, etc., and alpha 0, alpha 1, etc., are the corresponding coefficients to construct the polynomial. Now, these functions L0, L1, etc., basis functions at x0, then note that L0 will be found to be 1 at x equal to x0, because in that expression, for the expression of L0, this x minus x0 will be missing, all others will be there. Okay. And here x0, x0, x0 will be there. So, when we put x equal to x0, this and this will cancel, next will cancel, and so on, all of them will cancel, and we will get the value 1. At that same point x0, if we try to evaluate L1, then in the expression of L1, this term will be missing, this term will be there. Okay. So, at x0, when we try to evaluate, then we will get x0 minus x0, which is 0, right, and that means that the expression, and here it will be x1 minus x0, right. So, that means that L1, L2, L3, L4, all of them will be 0 at x equal to x0. So, that means that suppose this is x0, this is x1, this is x2, this is x3, and this is x4. So, that means L0 will be 1 here, 0 here, 0 here, 0 here, 0 here. L1 will be 0, 1, 0, 0, 0. L2 will be 0, 0, 1, 0, 0. At other places which are not the given data points, all of these expressions will have some other values, but at the jth data point, Lj will have value 1, all others will have value 0, and therefore, in this, when we try to equate the function values at x0, x1, etc., then we will find that at x0, when we try to put the value, then we will have alpha 0 into 1 plus alpha 1 into 0 plus alpha 2 into 0, and so on. So, we will get alpha 0 into 1 is equal to f at x0. So, immediately we will get alpha 0 as the function value itself at x 0. Similarly, alpha 1 will be the function value at x 1 and so on. So, at the data points we have this, that is as k is equal to I we have 1 and k not equal to I we have 0. Okay. So, that means that basically we are trying to solve a system of equations in which the coefficient matrix is identity this, and that means alpha I is going to be just f of xi. So, that means the function values are the coefficients here, alpha 1, alpha 0, alpha 1, alpha 2, etc. So, the Lagrange interpolation formula we get like this. Now, note that in this development from here to here we have done nothing which will not be possible for arbitrary data, arbitrary points and arbitrary function values. That means for any set of points and for any function values, this polynomial will always exist, and this is an nth degree polynomial. And earlier we have seen that whatever nth degree polynomial we can find to exactly satisfy n plus 1 data points, that has to be unique. Okay. So, that means we basically get this polynomial which is the same as the polynomial that we would have got otherwise through the earlier process, except that here we get the polynomial very easily without any difficulty, but then differentiation, integration, etc. will be more cumbersome from this kind of expressions. Okay. So, here you will find that we have got two interpolation formulae, one costly to determine with the basis functions 1 x, x square, etc., but easy to process afterwards. The other trivial to determine, the Lagrange interpolation, but costly to process later, differentiation, integration, etc. Depending upon your situation, depending upon your need, you will be in a position to frame the polynomial coefficients and the basis functions either this way or that way. If you want a formula, a methodology by which it will not be so costly to determine, on the other side it will not be so costly to process, you have an intermediate case also, that is the Newton interpolation, which is an intermediate trade off. There you have got the formula in this manner. Okay. So, in this case if you try to put x equal to x 0, you will find all these are zeros. Okay. So, you will get c 0 is equal to f of x 0. Then when you put x equal to x 1, you will have this and all others having a factor x minus x 1 will become 0. So, you will get another equation in c 0 and c 1 and so on. So, this will have a triangular coefficient matrix. Okay. So, it is easier to develop compared to the first case and more difficult to develop compared to the second case, Lagrange interpolation. On the other hand, the processing, that is differentiation, integration, etc., also will have intermediate computational cost. Now, another kind of interpolation is there which uses not only the function values, but also some of the derivatives. Such an interpolation is called Hermite interpolation. It has a lot of applications, because in many situations, many problems, you need to satisfy not only the function values, but the rates as well. They are part of the problem. That is, you cannot have a polynomial which changes in a rate which is different from what is already known to be the rate of change of that function which you are trying to model. This is one important point. The second important point is that sometimes with the help of interpolation which uses derivative information also, at certain points or in the locality, in the local neighborhood of certain points, we can establish, we can develop function approximations which have the required trends. So, therefore, Hermite interpolation is quite well used kind of interpolation. So, in this, what kind of data you will talk about? You will still have a few points, say x 0, x 1, x 2 up to xm, a handful of points at which you will use the data, and at every point the data may be function value and some of its derivatives. It is not even necessary that at every point you have the same number of derivatives to be used. It is possible that at x 0 the function value and 2 derivatives are given, at x 1 the function value and 1 derivative is given, at x 2 only function value is given, at x 3 the function value as and one derivative is given, that is possible. Now, whatever be the number of data items, function and its derivative values at every point. So, if you add up those number of those conditions, the total number of conditions that is given in terms of function values and their derivatives, that will equal one more than the degree of the polynomial that you can model. Why? Because these many conditions will give you the number of that many equations in the unknown coefficients of the polynomial, and if you have got n plus 1 coefficients in the polynomial, that means you can go up to nth degree. Okay, n plus 1 equations, n plus 1 unknowns. So, the number of the conditions will be one larger than the degree of the polynomial by up to which you can correctly model the function. Now, that way you can think of a function in which at this point 3 pieces of data are given, at this point 2, at this point 4, at this point again 2, and at this point 1. So, what is the total number of conditions that you have got? 3, 2, 4, 2, 1. That means 12 conditions. That means through these points, satisfying all these function values and derivative values that are given, you can make an 11th degree polynomial which will fit this data exactly. But then there are very strong objections to high degree polynomials as function representations. One is of course the computational cost and numerical imprecision, that is you will have to solve a 12 by 12 system of equations and that may be ill conditioned. So, that may lead to computational cost and numerical imprecision, but this is a minor objection. The major objection is that the high degree polynomials sometimes fail in their prime duty to represent the function well. Let us see how. As you know, a linear function of x either goes all the way up or goes all the way down or stays constant in the particular exceptional case. Okay. That is, if you remove this, then you will say that typically a linear function goes all the way down or goes all the way up. A typical quadratic function has this kind of a look. It goes down, takes one turn and then goes up, never takes another turn, or it goes up, takes a turn, then goes down. This will be the case if the coefficient of x square is positive. This will be the case if the coefficient of x square is negative. So, a quadratic function of degree 2 has two trends, once going down and once going up, right. A cubic equation, a cubic expression, a cubic function that is degree 3 will have at most 3 such trends, going down, then going up and then possibly going down again. I said at most because a cubic could also go like this, that is also possible. Okay. But then a cubic has the possibility of showing this kind of a trend. Okay. A 4 degree polynomial similarly will have the possibility of showing a trend of this kind or of this kind. Okay. This is the situation with a 4 degree function. Now, if you talk of an 11th degree function, that may have scope to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This kind of a profile it might show. That is, up to that much it can oscillate. That means that if your data are like this, it is possible for an 11th degree polynomial to give you this representation. which is a very bad representation, because through these data points the function that you were possibly approximating was this. It is a nice function, but because you allowed an 11th degree polynomial, the polynomial representation turned out to be this, which is matching the data exactly, but other than that it is doing nothing sensible. So, this is the prime objection to high degree polynomial representation of functions, that it may be failing in the prime duty, that to represent the function faithfully, that itself may be failed in a problem of this sort. So, that is why single high degree polynomial interpolation is something which we usually do not do. Then what do? We make piecewise polynomial interpolations. Okay. Simplest piecewise polynomial interpolation is piecewise linear interpolation. So, that means that if we have a large number of data points, like this, then one straightforward sensible way to find a piecewise interpolation of this could be to join these with straight lines and say that is a function representation, which is good enough for many purposes. So, for dense data where function values are available at a large number of close by points, there quite often we conduct piecewise linear interpolation. But we have to keep in mind that this representation of the function will not be differentiable, because at the corners from this side there will be some slope and from this side there will be some other slope. So, this will not be differentiable. Okay. So, piecewise linear interpolation is not differentiable. You can see that this formula gives you the piecewise linear interpolation. Between xi minus 1 and xi, you will get this formula which matches xi and xi minus 1 exactly, and it is a linear expression. Okay. Next higher interpolation typically used and very popular representation is piecewise cubic interpolation. Now, this is typically Hermite segments. What you do in this piecewise cubic interpolation is that at the data points you have got the function values and the derivative values, and then for every pair of points you try to frame a cubic with the help of two values here, function and derivative, and two values there. You see, function and derivative value at the two end points of every segment give you 2 plus 2, 4 conditions, and with those 4 conditions you can determine the 4 coefficients of a cubic exactly, and that you go on determining for every segment. So, for that what you will get? So, for every segment you will get, here you have got the function value and the derivative, here you have got the function value and the derivative. Okay. So, the cubic that you will be framing will perhaps be this cubic, but then the part of it which is outside this subinterval, that will not be used, and you will have only this much, right. And note that since the adjoining segment between these 2 points will also use this function value and this derivative value and match that data exactly, the trend of the function value here will match this segment up to the first order derivative, and this way you will get a curve, a function which is differentiable up to first order. Okay. So, you will have an exact interpolation with first order derivatives. So, the data for the jth segment will be function value at point j minus 1 at point j and derivative values at the same 2 points. With the help of these 4 pieces of data, you will get the 4 coefficients from here, because as you force these data values on this polynomial, you will get 4 linear equations in A0, A1, A2, A3, and then as you solve them, you will find that the coefficients will turn out to be linear combinations of these 4 items of data, these. Okay. And if the coefficients are linear interpolations of these, then you will get a composite function which is C1 continuous at knot points. That means, at the junctions of the intervals they will have first order continuity, that is the derivative is also first order derivative is also continuous. In between the knot points, that is during the segment, of course it will have infinite order differentiability because they are single polynomials. It is the differentiability at the junctions which we are trying to establish. The differentiability in the interior of a segment is of course up to whatever order you want. Now, this same formulation can be made in a general setup if we reparameterize in a normalized interval, say 0 to 1. So, that is quite often done and the result is something quite useful. Say the variable x, for that you have the interval say x3 to x4, j equal to 4, so x3 to x4. So, now between x3 and x4, if you put another variable t in terms of which you reparameterize the scale, okay, then at t equal to 0 you will have x3 xj minus 1, at t equal to 1 you will have this and this will get cancelled, you will have xj. Okay. So, the interval 0 to 1 will scale up to the x interval, that is xj minus 1 to xj, and then the function f of x can be talked of as f of x of t, which you can call as g of t, and then the g prime from this expression will be derivative of f with respect to x and then into derivative of x with respect to t, which you get from here xj minus 1. So, whatever is the derivative given in terms of f prime, that can be mapped in terms of g prime. So, with g mapped like this and g prime mapped like this, both functions of t, you will have these as the representative data. So, with these 4 pieces of data, you determine the cubic polynomial for the jth segment, right. Once you do that, you can note something interesting. This qjt you can write as the row vector alpha 0, alpha 1, alpha 2, alpha 3 into 1 t square t cube like this. And we have already seen that alpha 0, alpha 1, alpha 2, alpha 3 will be linear combinations of these 4 pieces of data, right. And with this fixed interval 0 to 1, these coefficients of these linear interpolations, these linear combinations are going to be constant, and therefore, you can have a0 alpha 0, alpha 1, alpha 2, alpha 3 as constant in terms of numbers, known linear interpolations of these 4 pieces of data, and that those linear interpolations, those coefficients will turn out to be a matrix, will constitute a 4 by 4 matrix W. In the textbook, there is a small exercise in which the steps to evaluate this matrix W is given, and I suggest that you attempt that problem. Now, with this representation, we can write for the jth segment Gj into W into T. Now, this way we have packaged the data, interpolation type and variable terms separately. That means, Gj, this vector, has nothing other than the items of data. This W has just constant numbers which reflect the type of interpolation that we have decided upon, that is in this case piecewise cubic. Okay. So, that cubic Hermite taking function values and derivative values at both the ends of the subinterval. Based on that decision of the interpolation type, we get this matrix W. If we had taken some other interpolation type, we would get some other matrix W there. And in the third segment T, we have the variable terms which will get their values at the time of evaluation of the function at a particular point. So, this modularity of representation we get if we convert, if we rescale every subinterval to the normalized interval 0 to 1. And the same expression, the same formula we can use for every segment of one composite curve and for every segment of every other composite curve for that matter. Everywhere we use the same matrix W of fixed numbers and the data changes, and at the time of evaluation we have to give these values of t. Now the question arises, that is, there are many situations where we have got the function values at several points through which we want a smooth curve, okay, smooth or say continuous curve, differentiable function passing through all these points. Now at these points, if we do not know the derivative values, then how do we supply it to a Hermite interpolation program, Hermite interpolation algorithm? The requirement of the first derivative becomes a problem. That is, if the problem as it is does not come with the derivative data, then how do we supply them? And also the question arises, why should we supply? Can we not say that we do not care what derivative is here? As the curve goes from this segment to this segment, we do not care in which direction it goes, whether it goes like this or this. All that we care is that whichever way it terminates at the end of this segment, exactly in that direction it should commence at the beginning of the next segment, and so on. Only this much we want to say. So in that case, we do not need to give the derivative values, but we can demand first order continuity. And if we do not want to specify the derivative values there, then we can demand not only first order continuity, but we can demand second order continuity as well. Note that when we were earlier giving the value of the derivative here at this point, then through that value actually we were supplying two conditions. One is that as part of this segment, the function should have this slope here, and as part of this segment the function should have this slope here. So at this point, through the derivative we were actually giving two conditions. Now that we want to omit that piece of data, all that we say is that we are going to demand first order continuity of derivative at this point. That is, whatever is the derivative here, we do not care. Similarly, whatever is the derivative on this side, we do not care. All that we need is that the derivative at this point from this segment and the derivative at this point from this segment should be equal. That means that the derivative value we are not concerned about, but derivative continuity we are concerned about. So when we ask for the derivative continuity at this point, then we are actually specifying only one condition. Now we have got a slot for another condition. So from where to get that condition? So we can say that at this point we want the continuity of the second derivative also. So that way, with the help of less data that we supply from our hand, that is derivative value we are not supplying, but we are demanding two conditions, first derivative continuity and second derivative continuity. If we do that, that is, we can do that when the requirement does not specify the derivative value. So when we do that, we can develop a function representation which is not only first order continuous, but second order continuous across the junctions, and that kind of an approximation is called spline interpolation. Spline basically, classically, it is a drafting tool to draw a smooth curve through key points which are already marked on the drawing board. Now from that particular drafting tool, the spline interpolation has got its name. How do we do this? Say there are n plus 1 points at which the data values are given. Now if the derivative value at the junction points are kj, unknown to us currently, then pj, the jth segment, say let us take j equal to 0, that means the first segment. Okay. So this segment can be planned or determined in terms of fj minus 1 fj kj minus 1 kj. That means function values at this point, and the rate here, right. So, in terms of these 4 quantities, we can determine this segment, right. Similarly, for this segment we will require the function values here, kj and kj plus 1, right. So, this segment is determined based on function values at these 2 points which are known, and kj minus 1 and kj. Similarly, the segment here, this one, can be determined based on function values at this point, kj and kj plus 1, right. If so, then the derivative at this point can be determined based on the same 4 pieces of data, and similarly on this side. So, apart from the known quantities, the slope here can be determined in terms of kj minus 1 and kj from this direction, and kj and kj plus 1 from this direction. All that we want to do is to equate these two. Okay. So, the first derivative is going to be same, because kj is used on this side as well as on this side. Okay. Now, the second derivative also we can evaluate and equate on both sides. That is, whatever is the second derivative here, that is in terms of kj minus 1 and kj, and the second derivative from this side will be in terms of kj and kj plus 1. So, these two quantities we determine and equate. Okay. So, Pj is determined based on these 4 quantities. Pj plus 1 is determined in terms of these 4 quantities. So, the derivatives, first derivative continuity is ensured because kj is used here and the same kj is used here. Now, if we develop the second derivative from this expression and the second derivative from this expression and evaluate both of them at the same point, at the junction point, that is at the end point of this interval and at the beginning point of this interval, and equate these two, that will give us one equation in kj minus 1, kj and kj plus 1 in these 3 unknowns. So, that means that at the junction 1, 2, 3, 4 we will get equations in k0, k1, k2, k1, k2, k3, k2, k3, k4 and so on. Okay. So, we will get n minus 1 such junction points, and at that we will get n minus 1 such equations in k0 to kn plus 1, and this equation system will be a tri-diagonal system, and as it happens it gives us a tri-diagonal, diagonally dominant system of equations. So, from the n minus 1 interior junctions we will get n minus 1 linear equations in the derivative values. These are n plus 1 values. So, to determine them completely we will need 2 values, 2 of these n plus 1 unknowns we will need, and then the rest of the n minus 1 can be determined. Typically, the derivative value at the beginning and at the end are supplied, and then the rest of them can be determined from these n minus 1 linear equations together, framing a diagonally dominant tri-diagonal system. So, this way we get a smooth curve like this, which matches the second derivatives at the junction points, and in between the junctions in a subinterval, of course, it is differentiable up to infinite order, that is of course known. So, this is called spline interpolation with C2 continuity. Now, in this same manner we can talk of multivariate functions also and interpolate them. That is, if we have a function of 2 variables. Okay. So, for that also we can have bilinear interpolations, bicubic interpolations, biquadratic interpolations, and piecewise bilinear interpolation. Whatever we did for one variable we can have for multiple variable. Okay. The spline also can be set in that same manner. Okay. Now, we will take one example, that is piecewise bilinear interpolation. For piecewise bilinear interpolation we have the domain structured in the form of a rectangular grid, right. So, we will typically have x0, x1, x2, x3, x4 and so on. Similarly, on this side y0, y1, y2, y3 and so on. So, suppose our domain is this, over which we want the function representation for this region, this rectangular region. So, for that we can have a rectangular grid like this, and typically for bilinear interpolation we typically want the grid to be quite dense. Okay. And then the function expression will look like this: constant term plus something into x plus something into y plus something into xy, which can be represented in this manner. Okay, one x here, one y here, and the coefficients here. Now the coefficients form a matrix. Okay. So, with the data at 4 corner points, function values only, with 4 pieces of data we can determine these 4 coefficients. So, as we put these 4 pieces of data with the corresponding values, x values and y values, okay, then we will get, this will be a known matrix, this will be a known matrix, this will be a known matrix, and we need to determine this matrix. Okay. So, pre multiplication of inverse of this and post multiplication of inverse of this will determine this matrix for us, which means the coefficients here. So, like this, for every small rectangular region we will get the function representation, and this will be continuous representation only, no differentiability. Okay. So, differentiability can be ensured if we have a piecewise bicubic interpolation and so on. So, we will omit all these details, because in the same manner you, as the representation of single variable functions, you can develop these, and everywhere we will have coefficients in the form of matrices, data also in the form of matrices. This is piecewise bicubic interpolation. Here you will need the derivatives, these derivatives, which again if you normalize, then you will scale in this manner as we did in the case of single variable function. Now, what is important for us at this stage is to have a quick look of what we have been doing all this while. Now, typically a common strategy of function approximation is to express a function as a linear combination of several known functions, that is a set of known functions which are called the basis functions. Now, the question arises, which basis functions to use? Similarly, we determine the coefficients based on some criteria. What is the criteria? That is the second question. Now, if we decide that our criterion is exact agreement with sample data, then we get one kind of approximation, which is interpolatory approximation, right, which we have been doing in this lecture. There is another kind of criterion, that is least square approximation. That is, we do not mind the some errors in the at the data points, but then what we ask for is that the errors all over should be limited. That typically we do when we have superabundance of data, that is more data than necessary to fix the coefficients. In that case, we expect error, and then we say that error square sum should be minimized. That is the least square approximation. Earlier in the linear problems, in the linear algebra segment, and then in the optimization segment, we have seen how we conduct least square approximation in the modeling of functions. Least square approximation is based on minimizing the sum of squares of errors. Now, when these sums are sums of infinite terms organized, arranged very close to each other, then that sum is replaced by integrals. So, even that is a kind of least square approximation, which we will study after our study of differential equations. And around the same time, we will study the third criterion of function representation also, that is minimax approximation, which also has a certain advantage, which also has a certain application. There we do not try to make exact agreements with certain data points. We do not want the overall least square approximation. What we want is to keep the largest error within a limit. That means we try to minimize the maximum error, and that is why that kind of an approximation is called minimax approximation. So, after the study of ordinary differential equations, when we take up our topics on approximation theory, there we will consider this kind of an approximation also. Now, this is the kind of approximations that we can talk by choosing different criteria. Now, which set of basis functions we use? One possible choice which we have been doing in this particular lecture, in this particular lesson, are polynomials. Okay. So, in this lecture we have done single polynomial which with basis functions as 1 x, x square, etc., then Lagrange polynomials, then Newton approximation, or piecewise polynomials. So, polynomials is one large class of basis functions that can be used. Sinusoids, sines and causes, sines and cosines are another set of popular basis functions which give us Fourier series. Orthogonal eigenfunctions, which will be encountered here, are another fertile area of choices of basis functions. And then sometimes field specific heuristic choices are also possible, the kind of choices we have been talking about when we were talking about least square approximation in the context of optimization. Now, all these are sensible, all these are proper choices of basis functions, and we choose the set of basis functions and we choose the criterion depending upon what is our field of application. Now, one important issue here is that we have been talking about the approximation of functions of this kind, f of x, right, and then f of x y, right. Now, consider this independent variable, we will just change the names and then see what kind of interpretations we can make. In place of this independent variable t, x, suppose we put t, and for this function in place of f we put x. X of t will be a function of parameter t. Now, similarly, y of t can be another function of parameter t, and z of t can be another function of parameter t. Now, all these we can do exactly the way we have been doing for function f x, and now these three functions can be taken as x coordinate, y coordinate, and z coordinate of a point or a curve as t varies. Okay. So, enclosing it like this, we get this, right. So, this is a vector function of a scalar variable t. Now, with this kind of a setup, with the same interpolation tools, we can actually model curves in 3D space. Similarly, the bivariate functions that we have been talking about, in terms of such bivariate functions, we can model triplets of such functions, that is, we can model vector functions of two parameters u and v, and that way with a lot of data over the surface we can make a representation of the surface like this surface as functions of two parameters u and v, and with the help of that we can model surfaces. So, typically curve and surface modeling is one large area which stems from this kind of interpolatory or other function approximations. For example, suppose you have got a large number of data points in 3D space and you want to find out the analytical representation of a surface on which all these data points lie. Then what you can do? You can say that suppose I have got a bicubic expression of u and v, and a bicubic expression, not just one expression but three expressions, one for x coordinate, one for y coordinate, one for z coordinate. So, you can say that we have got a bicubic vector function R x y z, that means three scalar functions and each of them bicubic with two variables u and v in hand. That means you have got four by four matrix like this. So, this will give you a bicubic expression. Now, you have got three such expressions for x of u v, y of u v and z of u v, and then you want to determine the three 4 by 4 matrices sitting here for the x coordinate, y coordinate and z coordinate, and with all the points that are given to you as points on the surface, you can use those points as the set of data, and then you can frame equations for x coordinate, y coordinate and z coordinate, and from that you can determine these three 4 by 4 matrices. Once you determine these 4 by 4 matrices, you have got x coordinate, y coordinate and z coordinate as functions of u v with known coefficients here, and that means that you have got a complete analytical representation for the surface for which the data was just a lot of stray points. So, this way you can do a lot of curve and surface modeling with the help of these kinds of interpolatory formulas. So, for this particular problem, you can also do a bicubic approximation based on the function values and their derivatives at the endpoints. Okay. So, in that case you will have the data points, the values of the function, and then their u derivatives, their v derivatives and the cross derivatives, that is del 2f by del x del y. This kind of data you can use to model bivariate functions, and when you have vector functions like that with three scalar bivariate components, you have got a model of a surface. So, such curve and surface modeling are often done in the case of computer aided engineering design or computer aided geometric design. So, some of these examples, some of such examples are there in the exercises in the chapter of the textbook, and I will suggest you strongly to attempt some of these exercises to develop an ability to work with such approximations. Thank you.